Okay, so good afternoon, everyone. Today is the fourth lecture, and we'll be looking at the BJT transistor. So we have, in the last two lectures, we have looked at what is a BJT transistor, and we've looked at the forward active mode. We also looked at the cutoff mode, and we determined some basic equations which relate the currents, the collector current, the base current, and the emitter current. And we looked at it both for the thanks. I am recording the class. I have already started the recording. So we looked at the relationship between the three currents. We also looked at parameters called as beta and alpha, and we looked at these things for both the NPN transistor and the PNP transistor. Okay, and we introduced this for the BJT. Now, what we are going to do in today's class is I think this will kind of clear some of the doubts that some students had in the previous classes. So we are going to look at, if you want to have a brief outline, what I will try to do today is to introduce the large signal model of BJT. We will look at it. And secondly, we will look at what is called as the reverse active mode of the BJT. And thirdly, we will combine these two together to look at what is called as the Ebers-Moll model of BJT. Okay. So I think these are the three things that we will look at. If possible, we will touch upon the saturation region of BJT. We might try to do that, but I'm not sure we'll have the saturation mode of BJT. This might get pushed out to the next class. Okay. All right. So let's get started. So we are going to look at what is called as the large signal model of BJT. Okay. Now, many of you might have this question: why am I talking about a large signal model? Is there something called as the small signal model? The answer is yes. We will be looking at the small signal model eventually, maybe in a few classes from now. But right now, we are going to concentrate only on what is called as the large signal model. The distinction between the two we will look at when we move to the small signal model. Okay. All right. So basically, what is a large signal model? It is to model the voltages and currents of a BJT at a more abstract level. Okay. Where there is no limit, let me put it like this: no limits on the absolute or relative values of the V's and I's. Okay. All right. You will appreciate this once we move to the small signal, but just let me put it here. Okay. So we say that we have this, three-terminal device, which we are calling it as the BJT transistor. We have the collector terminal, the emitter terminal, and the base terminal. What we are going to do is to form an equivalent model for this. Okay. Now, what kind of model can be formed? We saw that there is basically, this is the collector region, base region, and emitter region. This is your N, P, and N, right? And we know that the base emitter junction is a forward bias diode. So let's start with that diode. Okay. So I'm saying that this is going to be my base terminal. This is going to be my emitter terminal. Okay. And between the base and the emitter, I have a diode, and this diode current, if I can call it the IDE, okay, the diode emitter diode current can be written as what? Let me call it ISE exponential VBE by VT. Okay. Now this ISE is different from IS. this is a diode which has a voltage across it called VBE, okay, defined like this, and the current is the saturation current of this diode, okay, ISE, e to the power of VBE by VT. Now, how do we relate the, how can we bring in the collector terminal? Okay, this is an equivalent model. Okay, when we say a model, it kind of captures the characteristics of the device, but it is not a reflection of the exact circuit. It's a model that you can use for your calculations or your design purposes. Okay, so we said that this can be, the base to emitter can be modeled as a diode which is forward biased, which has a certain, you know, reverse saturation current, and with a e to the power of VBE by VT. Now, how can we model the collector terminal? Collector terminal can be modeled as a dependent current source. Okay, the dependent current source which is flowing in this direction, and what is the value of this dependent current source? It is nothing but alpha times IE. Let me just remove this. IE can be written as, okay, this is for the forward active mode. You have alpha times IE as the dependent current source between the collector and the base junction, collector and the base, and between the base and the emitter you have a diode, and this relationship, this is the relationship for the current. Okay, now this is an equivalent model. So suppose you want to do, you are building a circuit around this BJT, and you want to calculate the DC currents or the DC voltages that you are going to get. Let's say you are sticking a resistor at the collector node and at the emitter node, and you have some other network. You can basically use this, and then you get a more abstract circuit model, a circuit model or an entity which you can solve to get the equations that you need or the results that you need. Okay. Now, what is this particular thing? Now, this alpha times, this is one way of writing. Okay. Another way of writing is what? Now, how is this alpha? What is this collector current? Okay, another way to write this is also to say that the BJT can be written the same thing. I'm just writing different equations here. You have a dependent current source and you have a diode. This is your base, this is your emitter, this is your collector. Now this current source value I can write as some IS times e to the power of VBE by VT. Correct. This is from our usual analysis. I mean, what we have already looked at. And what can we write as the diode current? This is going to be your VBE. Okay. Now, what is going to be your diode current, emitter diode current? We can write as IS divided by alpha. Okay. E to the power of VBE by VT. In other words, the ISE that we have defined in the previous slide can be written as the IS that we use in the collector equation divided by alpha. Okay, is this clear? This is a large signal model of a BJT. Any questions? I think many of you had the doubt, like what is this IS? How is it related to? I think I explained it as last class itself. I think this large signal model, kind of clears all your doubt. It is a diode. The emitter current is actually the diode current. Okay, the diode current which is given as some constant ISE. Okay, which comes from the diode equations, e to the power of the voltage across the diode divided by VT, which is this particular equation, and the collector current is defined as alpha times this IE. In other words, it can also be equivalently written as, this is the IC equation, the collector current equation, and from there you can bring it like this. Any doubts? Any questions? Is this clear? Yeah.
So here ISC is the reverse saturation current of diode.
The diode, yes. Reverse saturation. ISE. This is called as the reverse saturation current of
BE diode.
Yeah, EB diode or BE diode, whatever. Okay.
Then IS?
IS is how you write it, IS is nothing but alpha times ISE, where IC is defined as IS e to the power of VBE by VT.
Yes.
Okay. Okay. It's as simple as this. Okay. So now all confusion cleared. The current is determined by the diode, and usually you will see that as you, the reason why I keep talking about collector current rather than the emitter current is that once you start designing, you will mostly look at the collector current equations. Okay. And in fact, like if you want to be even more accurate, you would basically say that, IE can be written, or rather IE can be written as what? ISE e to the power of VBE by VT minus 1. You'll usually have that minus 1 factor, but the approximation, kind of makes you to neglect the minus 1 factor. Okay. But usually the collector current is of more interest in circuit design, and that's why, instead of having all these other factors coming in, we just put one IS. Anyway, it's some proportionality constant which has been scaled to accommodate the alpha factor. Okay. All right. Is it clear?
So I have a
Yeah.
doubt. So,
Yeah.
so you said that it's an abstract concept that we can only use for use in like solving equations and stuff for making
Correct.
the circuit clear.
Right.
But we can't use this in the actual circuits. So it will not perform the same manner as the transistor does.
Excuse me. I mean, a model is expected to follow the model. Okay. So what I'm trying to say as a model is, yes, it is supposed to be fairly accurate. It's supposed to be a fairly accurate representation of the transistor. Okay. But this is not a perfect representation of the transistor because there are other effects also. Okay. We'll start looking at the capacitances which are involved in the circuit. For higher frequency application, we will bring in that model, and we will also bring in the output impedance model, okay, to account for the early effect. So all those things are there. Okay. Now you cannot say that a BJT is just this. It is a model of a BJT. Okay. The axles, we started with the axle structure, and this is what we use. Okay. And you will see there is another hybrid pi model which we will study a little later, and which will be used for all your small signal equations. This is one way to model. Okay. And there are other things that need to be modeled which are left out. This is for a large signal understanding, and we kind of leave it at that. Okay. So probably as we go along the course, you will start, appreciating what is a model, and what are the shortcomings of each model. Okay. It is not a perfect representation of all that the device is. Okay. But this is a large signal representation which is required for large signal analysis purposes. That's it. Okay. Yeah. Okay. So there is another way in which this large signal model can also be looked at. Okay. Which is which is basically pretty much the same thing. Only thing you kind of basically it's the same thing. So probably I'll not go into it. It's just like, put a diode here and then, the current source here. It's just, shifting things around. Some books will give you this model also. So I'll just leave it, but it's essentially the same thing. Okay. Now the next topic that I want to talk about is what happens, what is called as the reverse active mode. Okay. Till now we have been looking at what is called as the forward active mode. What is the forward active mode? We said that the base emitter junction is forward biased and the base collector junction is reverse biased. Okay. Now what will happen if you kind of do an inverse of the whole thing? Okay. Suppose you forward bias the collector base junction and reverse bias the emitter base junction. What do you think will happen? Okay, let's
Maybe
kind of go into this. This is your N and P and N. This is your emitter, base, and collector. You have these three terminals, right? Can you guess what will happen? I mean, it is okay if you are wrong. If you are, yeah.
like the current value will be less in the opposite direction when compared to the forward active mode.
Okay, current direction, current will be lesser. Why do you think so?
So because the area, the region, because the doping, the collector and emitter terminal may be changed like literally, like the electrons move from the collector terminal.
Correct.
So
Yeah.
so maybe because now the minority charge carriers will be the main current players.
Oh, well, it's still an NPN, and so what will happen is, let's say you are forward biasing this particular part, and you are reverse biasing this particular part. Correct. Okay. So this junction is forward bias. Now what will happen is, yes, you guys are kind of almost there. I mean, pretty much right. So you are saying these electrons are going to move from collector to the base, and then swept across this thing into this one. Okay. So as someone pointed out, the current flow will be lesser because first of all, first reason is the doping in the collector region is less than the doping in emitter region. Correct. So that itself will kind of give you a different current profile. Your IS and everything will change drastically. Okay. Now the actual structure of so this is how we usually draw and explain that a BJT is, functioning and so on. It is as if it's one rectangular block with some, three sections. In fact, what happens is the way in which if you were to actually fabricate in silicon and look through a microscope, the way in which it is done is something like this. You'll have the emitter here, and you'll have a thinner base layer which is surrounding that emitter. This is the top view. Okay, I am drawing the top view of actual BJT. There are other ways of implementing a BJT which is also there. Okay, okay, I need a little more space. Okay, let me say this the emitter, and I have a thinner layer of base, and I have a bigger collector surrounding it. Okay, so the actual common way of fabricating the BJT device is not necessarily in this way. Okay, where you kind of have like blocks of NP and N kind of attached together. The way in which it is most commonly implemented, there are other implementations, there are some vertical devices, other implementations also. I'm not going into that. The common way of doing it is in kind of concentric ways. Okay, first you have the emitter in the center, and then you have a layer of base around it as a concentric circle, and then you have the collector which is surrounding it. Now if you do a cross sectional view, okay, remember this is the top view. The cross sectional view, how will it look like? Let's say I'm going to slice it here. Okay, the dotted line is where I'm going to slice. How do you think it will look like? It will look something like this, right? You have the N region, which is the emitter, and you have the P region, which is the base, and then you have a wide N region, which is the collector. This is your cross-sectional view. Now, because of the way in which the device is engineered, okay, somebody asked me a question, can you change beta? After it is fabricated, you can't change beta. But before it is fabricated, if you are a device engineer sitting in, let's say, Intel's foundry or TSMC's foundry or ON Semiconductor or something like that, you are given the freedom to, or you are given the task of engineering this device. Okay, basically it's device physics. You will align all the doping concentrations, the width of the base, the width of the I mean the dimensions of the emitter, the collector, everything. You will engineer it in such a way that the forward active mode is preferred. Okay, so it is done in such a way that the forward active alpha is close to 1 and the forward active beta is fairly high. Okay, now when you try to use the same device in a reverse mode, what happens is it is a suboptimal performance. Okay, so we can define what is called as the alpha R and the beta R. Okay, so this is the IE to IC ratio in reverse mode, and this will be what? IE to IB ratio in reverse mode. Okay, because now the collector is acting as the emitter and sending the charge carriers, and the base emitter junction really doesn't do anything much. Okay, now this, if you define this alpha R and beta R, now what happens is, for a typical device, okay, the alpha F and beta F are optimized. Okay, and if you take that device and operate it in a reverse mode, your alpha R will be somewhere in the region of, it can range something like, let's say 0.01 to something like 0.5. Each device will be somewhere there, but this is the range over which your alpha R can be. Okay, even your beta R, they say it can range from something like 0.1 to maybe 1 or 2 or something like that. So your beta is very small, your alpha R is even more small. Okay, in other words, we can kind of say a summary statement, okay, which we can write like this: the BJT is not a symmetrical device. Is this clear? That is, collector emitter cannot be interchanged. Okay, it is not a symmetrical device. You will see that when we talk about MOSFET is a symmetrical device. Okay, so you will appreciate this fact when we start talking about MOSFETs. MOSFETs, you can interchange the drain and the source terminals and nothing will happen. It will work just the same. Okay, but whereas the BJT is not a symmetrical device, and therefore interchanging collector and emitter will not give identical results. Okay, so with this we will kind of close the book on reverse active mode. It is not a preferred mode. Okay, it is basically you build the device to operate in either the forward active mode or cutoff mode or saturation mode. This is like, a naughty kid taking a toy and, doing something which it is not supposed to do. Okay, if you do that, you will with some alpha R, beta R, which is looking like this. All right. Now, if we have to model it, let's say a large signal model of reverse active mode BJT. Okay, what can we do? What do you think is the thing? How can we model it? Let's say we have the same 3 terminals. This is the base, this is the collector, and this is the emitter. Now, how can we model? Where is the forward diode put here?
Collector base.
It is the base and the collector. So we can say that there is a PN junction diode which is sitting here. Okay, and what can we say? We can say that there is a dependent current source which is going in this direction. You can see that the current direction is in the opposite direction of a forward active mode. Okay, and we can say that this diode current, okay, IC diode current can be written as what? Some ISC, which is the diode's reverse saturation current constant, e to the power of V. What is the subscript here?
BC.
BC. VBC divided by the thermal voltage. Okay. Now, what can be this current source value?
Alpha times
Alpha times R. Alpha R times IC.
IC.
Okay. This is a large signal model of a reverse active mode BJT. Okay, is this clear? Any doubts? And just to be clear, here we talk about the emitter current as being some Is e to the power of VBC by VT. Okay, and here how is the Is related to ISC? Is is equal to alpha R times ISC. Okay, just like how we did for the forward active mode. Okay, just keep these things in mind. Okay, is this clear? Any doubts on the reverse active mode? Okay, no doubts. Wonderful. Okay, now we have looked. Yeah.
Sir, I don't have doubt in reverse active mode, but
Okay.
I'm like confused about what's the actual meaning of this large signal in this large signal model. Like,
Okay.
can you give an example where, like, how is it different from the normal?
From small. Okay. So, yeah, if you wait for some more classes, you will get a clearer picture. But since you want me to just give you an example, okay, let me just say as a postscript here or a footnote here. So, in a small signal model, what happens is the small signal model is valid. There is a condition, okay, where the signal amplitude is roughly less than, let's say, 10% of the absolute bias value. Now, if I have to explain this, I have to take a little longer lecture. So, to just give you a one-line answer, in the large signal model, you don't have any conditions like this. In a small signal model, you will assume that the signal amplitude that you're talking about is kind of negligibly small compared to the bias value at which your analysis is done. Okay. Here, what basically we mean is there is no limit on this VBE. Okay. This VBE can be 0.5, 0.6, 0.7, 0.8, 0.9 also. You'll have larger current. This model is valid. All right. But whereas the VBE, you will write it as a smaller subscript. Okay. For a small signal, you will say that, let's say, for example, your bias value is 0.7. In a small signal model, you will see that VBE should be less than 0.07. Okay, only then that model is valid. Okay, otherwise that model becomes invalid. You'll, in other words, that if you use that model for larger signals, you will end up with erroneous results. Okay, whereas no such conditions are applied for a large signal model. So here, even if you say the VBE is large, okay, it's a DC value here that we talk about, it is still fine. Okay. I think I can explain only till here, because otherwise then I have to go into the concept of biasing and signal. So the composite signal will be written as a DC bias plus the signal. Okay. And for example, let's say your input to your amplifier will be written as some DC bias plus some small signal. For example, let's say it is A sin omega t. Here we will see that this A should be less than 10% of VDC. Only then that small signal model will be valid. Otherwise, it will be invalid. All right. We have not yet come to applying an AC signal to the amplifier and looking at its response. We will be looking at all that, but right now, I don't want to go into that because we will go step by step. Okay.
Yes, sir. I've got an idea.
Okay. Good. Now, what I want to do now is let's go into what is called as the Ebers-Moll model. Okay. Now, typically this is supposed to have been covered in your second semester. Have you done this? You have not done this,
sir.
right? No. Okay.
No, sir.
Yeah. So this is supposed to be covered in the second semester, and usually in this course I don't take this model and so on. But because that was not covered in the last semester because of all this dislocation that happened with the pandemic, I'll kind of cover this in this lecture in this course also, okay, just for the sake of completeness. Okay. Now, what is an Ebers-Moll model? It's basically a comprehensive model of a BJT. Okay, what is the comprehensive model of a BJT? Basically, it will cover all the 4 regions. I have still not talked about the saturation region, but let that be there. Okay, what are the modes that we talked about? Cutoff mode. Then we looked at the forward active mode. Now we looked at the reverse active mode. And we will try to look at saturation mode today if possible, or if not tomorrow, or in the next class. Okay, the saturation mode. Now these are the 4 modes in which your transistor can possibly work. It covers all the combinations. Okay. Now this model can capture the effects, capture the performance in all these 4 modes. Okay. And don't think it's going to be very great or complicated or difficult to understand. It is very, very simple. We looked at 2 large signal models today, right? One model for the forward active mode, one model for the reverse active mode. What we are going to do now is basically put both together. Okay, put both together, it can handle all the 4 modes. Okay, so let's put both together. Let's start with our forward active mode. How did we say that our forward active mode was behaving? We said that we had a diode. Let's say this is our base. Okay, this is our emitter terminal, right? We had a diode here, and we had a dependent current source in this particular direction. Okay, and this is plus minus VBE, and let's say there is a current flow here, which let's say we label it as IDE. Okay, IDE. We know what is the value of IDE. What is the value of IDE? IDE can be written as ISE exponential VBE by VT, which can also be written as what? IS divided by alpha F e to the power of VBE by VT. Okay, that's it. Now let's bring in your reverse active model. What is the reverse active model? We basically had a diode here, which is in this direction. Okay, and this is your collector terminal. Now let's put one more dependent current source, but the direction is in the opposite direction. Okay, and what did we say was this the value of the current source? Let's say, let's finish this here. This is I alpha. Let's just write in terms of alpha, makes life a little easier. Alpha times ID. Correct. IDE is here in the forward active mode. Alpha times IDE. Okay, and so if I were to look at the current direction of the forward active mode, this is the forward active mode current direction. Correct. Now let's look at the reverse active mode. We said that let's say this is going to be IDC, and the value is something like this, VBC. Okay, and what is IDC? Is ISC exponential VBC by VT. Can also be written as what? IS divided by alpha R e to the power of VBC by VT. Since it's the same device, this IS is the same. Okay. Now what happens is, this is our equation, and what can we write here? This can be written as alpha R times IDC. Okay. This is what is called as an Ebers-Moll model. Is this clear? All we did was took the large signal model of a forward active in the forward active mode, took the large signal model in the reverse active mode, and just put both together. Okay, and we basically got this model. Okay, and what we have done here is we have kept this IS as constant for both the models, and the ISE and ISE are different. Okay, ISE is given as IS divided by alpha F, and ISC is given as IS divided by alpha R. Okay, so this factor alpha captures the effect of all the what we talked about, the area being different, the doping being different, and the junction area being different, and all those things. Okay, so this is how it works. So any doubts, any questions here? Okay, it is very simple. Okay, all right. Now what we will do is, let's just write a couple of equations. Okay, what we will write here is basically, how can we define IE here? I'll probably start writing here itself. Okay, IE, the current which is going to come out of this emitter terminal, what can we say? It is IDE
IDE minus
alpha R times
alpha
I.
IDC.
That's it. Okay. What can we talk about the current which is going into the collector? Because we are kind of assuming the forward active mode. Okay, or we are sticking to that convention. Okay, and we want to do it. So what can we write about? What can we say about IC? IC can be talked about as minus IDC plus alpha F IDE. Okay, and IB is going to be what? IB can be written as what? It is basically IDC minus
IDC plus IDC plus IB.
It is basically the base current flowing inside. Okay, IB can be written as, like, once you combine the alphas and the factors, you can say it is 1 minus alpha F into IDE plus 1 minus alpha R into IDC. Okay, that's it. Now you can substitute for IDC with all these exponentials and you can get a bigger equation. Okay, you can substitute it and get the equations for IB and IC and IE. Okay, with all the exponentials. Now what happens is, depending on which mode it is, that particular current will be dominant. The other thing will be very negligible. For example, in the cutoff, how does this model help us? In the cutoff mode, what happens? Everything is turned off, right? VBC is 0, VBE is 0, and therefore all the exponentials will go to 1. Okay, you will be left with only the reverse saturation currents flowing around, right? So it models our cutoff mode. Okay, at slightly higher potentials, okay, whether it is in the forward active mode or reverse active mode, that particular branch will start taking over. The other mode will go into a negligible mode. Okay, for example, if you are in the forward active mode, your VBC is negative. Correct. Let me go here. In the forward active mode SAM, okay, what happens is VBC is negative. Okay, and therefore the IDC that we talked about will be negligible, right? And IDE will be prominent. In the reverse active mode, VBE is negative, which will give rise to IDE being negligible and IDC being prominent. Okay, so this model can take care of all the modes. We still haven't talked about saturation mode. Okay, now what can we say about okay, saturation mode? Let me take in the next class. Okay, before that, if there are there any questions, doubts? Okay, so if there are no questions and doubts, let's try to solve at least one problem today. Okay, so let's say we have an NPN transistor. All right, and for a VBE of 0.7 volt, you get an IC, the collector current, of 1 milliampere. Okay, now suppose you want an IC of 0.1 milliampere and an IC of 10 milliampere. What will be the corresponding VBE? Okay, you can take the thermal voltage to be around 25 millivolt. Okay, at room temperature. Some books will say 25 millivolts, some will say 26 millivolts, doesn't matter. Okay. Can you calculate and tell me? Let me also give you another problem. With this, we will conclude our class. Okay. We have a NPN transistor which is measured. Okay. And the measured values are like this. The base current is 114.46 microampere. The emitter current is measured to be 1.46 milliampere. Okay. And the VBE was measured to be 0.7 volt. Now you can calculate what is the alpha. Just write it as calculate alpha, calculate beta, and calculate IS. Okay. So with this, I'll wind up today's class. If there are any questions, you can ask me. If not, like you can work out these two problems. Just let me know the answer and we can conclude.
Can you go